Hey, I'm really enthusiastic about sharing this project with you. I'm going to tackle a Fender Princeton 112 Plus solid-state amplifier that has 4 issues. First off, when you turn the power on and off on this amp, it can make an extremely loud popping sound. And I found some good information that I'll share with you to deal with that, and I'll walk you through executing this change. Related to that, there's very little effect on the volume control when you go from 1 to 10. Everything kind of happens from 0 to 1. So I'll show you a fix for that. So that's 2 things. There's also a broken input jack for the Footswitch. It has a front panel jack for plugging in a Footswitch, which is a handy feature. Problem is, if these amps keel over and hit something plugged into those jacks, it can break them. And then the 4th item that I need to work on is the reverb unit is really underperforming. So we'll take care of all 4 of those things. To start this repair project, you need to take the chassis out of the case of the amplifier. So you take your trusty Phillips head driver. There are 4 screws on top that you're going to want to take out. And then there are 2 on the sides, just the ones towards the rear. You don't want to take the forward ones out unless you're trying to remove the front panel. Alright, and then it's also a good idea to have a bin that you can put all the components in, like knobs and the screws that you take out. And then the other point I want to make is where these screws go. This is the front panel, and there are 1, 2, 3, 4 screws that go through the top into these locations. And then 1 on this side and 1 on this side. Try and save you from making the mistake I made when I first took it apart.
Alright, so I've got the chassis out of the Princeton amp, and this is that Footswitch jack that had lost its nut, and some weird things were happening, and you can see it's sitting way back compared to the other ones. That might be the way the PC board's laid out, but I don't think so. It's like dead loose in there. The solder joints are completely shot. It might make it easy to get out. Probably still have to remove some solder, but the idea is to replace it. Yeah, see what's going on. I've got a replacement part that I purchased online, and it's supposed to be a right angle jack for a Fender circuit board, so it should fit right in there. We'll see how that goes. So let's get this out of here and see what we're dealing with. I'll probably have to pull screw here, and pull some of these nuts and the knobs off in order to get this out the rest of the way. Should be fun. I've got the nuts off the jack here and these 4 jacks here, and I've got the knobs off. They're all in a little pile here, and the knobs, under the knobs, there are these little spacers. So there are, I think it's 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 knobs. They look like this, but there are these spacers under them. There's a little sleeve up. Yeah, not quite focused, but the small diameter, there's a little neck down there. That smaller portion goes in, sort of centers the shaft in there. So I've labeled the connections. I know that I took the picture of the speaker wires, which one goes to which of these lugs here. I think the white one's on the right, whatever the picture shows. I got all these screws out. There's the 2 here I pointed to in that still photo. There's 1 here and 1 here, and then So I was wondering what was holding it, and it's these 3 screws here go into the heatsink. There's a big block of aluminum underneath the board. I don't know if you can see it very well. Well, I've just about got the PCB free. It's tethered by the reverb lines, so I'll need to pop that grommet out. But I wanted to give you a heads up on something I discovered, that this heatsink was floating. These are just clearance holes. There's some goop of some kind to help with thermal contact resistance, so that you get heat flow better with that goop there. But it's fascinating to me that the 3 screws that I took out actually are threaded into this plate that rides on the board. And this big heavy bar of aluminum just goes along for the ride. When the screw comes out, this just goes flying around. So you can learn from my mistake. You don't have to make that mistake yourself. Whatever greasy stuff is on here, I'm just going to leave it on there. It's probably a good enough thermal conductor. And I'll try and leave that in pretty good shape there. I'd like to clean it all up and put something else in there, but we'll leave it as the factory had it for now. This is the guy that's in trouble, so I might be able to So this is where he solders in. I'll get the solder off of there. I might be able to do it with the play that I have. Alright, it's with mixed emotions I show you my technique for this. I'm not the best at desoldering components, but the basic idea is you take some solder wick. I think I bought this online. I like to use a fair amount of flux. This is rosin flux. I try and go with just lead free. Now I'm trying to take solder off, right? So why am I holding up solder? You want to have a ball of solder on the tip so that you get the heat to flow. So I've already taken a couple of passes at this lug of the Footswitch jack. And I want to see that solder flow, and I want the wick to pick it up. So I've got a fair amount of it out of there. It goes smoothly. You can sort of get the solder on the board to melt and just drag that wick along. You'd like to just get all the solder out of there and get the component out clean without any damage, especially to the board. There's another technique where you use basically a heat gun, source of very hot air. So you can buy desoldering systems that are very nice, pretty expensive. So a little bit of wick and good luck will go a long way. I've always loved the smell of rosin flux when it vaporizes. It's probably not really good for you, but there are small pleasures in life. Okay, so this is not dead loose now, but it's getting there, and I'll keep at it. That's the basic technique. Alright, I got this out pretty cleanly. I'll have to touch up the solder pads, but I'm pretty happy with the way that went. No damage that I can tell to the traces. There are no traces on this side. That made it a lot easier. When you've got double-sided boards, it can be a real devil to get the solder off both sides. That's where those heat guns really come in handy. So when I took this out, looking at it, I can see that there's a lot of damage that occurred to this pin right here. So that was the forwardmost pin, and this thing took a shot, obviously, that pushed this in like this, and that splayed the lug out this way. It's kind of amazing that these other guys were still soldered in place, but oh, now that I look at it, they actually careened way forward. So this thing was just like destroyed. Amazingly, it looks like the replacement part is approximately correct. Alright, so I did a little investigating. It's hard to get this thing in here. I took a magnifying glass and looked at the slots here, and it looks like they're pretty clear. So then I got worried about, or I got thinking about dimensions of maybe the new part had different dimensions than the old one. I don't think it's that. It looks like as a part of the manufacturing technique, they make the front and back contacts sort of spring-loaded. They're little springs. I don't know if you can really see it very well. I'll try and take a close-up. But so I had to do a little bit of filing on this forward tab, where the tab goes through the PCB. Dimensions a little bit different from the jack. And now that I got it popped in there, the barb that kind of springs out, it's got this so I can't take it back out too easily. But so here are the steps that I took to get to this point from the last video. So I took my flux and I took my solder wick and I dragged the solder wick through the flux with the iron. You can see the smoke coming up. So basically really loading up the flux with the wick with flux. And then made sure I got all the metal off of there, but just very briefly, if you overheat these pads, they'll pop right off of the board. You don't want that. Anyway, after I did that, I had some residue, some kind of junk in the hole here. And what I actually did was file it a little bit very carefully with a jeweler's file, because the dimensions were wrong. So when I measured, the old jack, and of course it's like all destroyed up here, and then compare that to the dimension on the new jack, and then looked at the holes. The hole spacing was a little different. The slot here, it was a little too far this way. So you can't really bend that tab, or it ends up looking like this. You don't want that. So by increasing the length of the slot this way a little bit, I was able to get it to pop in. End of story. And if I actually scrape the brush through there, I can get it on there. Okay. Notwithstanding everything else, when it's all soldered in, I want it to be flush to the board. And actually, that's where those barbed lugs kind of come in handy. There, that flowed nicely. There we go. Those are some good hot solder joints. What do I mean by a hot solder joint? Yeah, the iron's always hot, but a hot solder joint just means that I've got good wetting to the solder pad. Getting a lot of reflection, making it difficult to see. Alright, so with the solder flux mostly cleaned off, I used some alcohol. And actually I used the same wire brush that I had used to spread flux, but I cleaned it up and then I got a bunch of flux off of there. Alcohol is pretty good for getting rosin flux off. And man, I gotta tell you, I'm getting really annoyed at the camera between the memory cards filling up and the batteries, and now the furnace is kicking on, of course. But so there's a lot to be thankful for. This job went pretty well so far. I got the new jack in here for the Footswitch. It looks like dimensionally it's in pretty good shape. I'll check it against the panel. It's a different style. This had transparent pieces, but that doesn't mean anything to me. It seems like it's going to do the trick. But it's a pretty clean PCB. While I have it out, it's tempting to recap it to some extent, but might be a little young to be doing that. I don't need to necessarily make a career out of this project. Hey folks, back at you with the Princeton 112 Plus amp improvement project. So I've replaced the Footswitch jack. That was pretty straightforward. This is much better. I decided to go ahead and pursue
tackling the popping sound when you turn on and off the amp, and also improving the reverb performance. So on the popping sound, when you turn on and off the amp, I'll call your attention to the volume control. It affects the feedback, the gain resistor on this op amp. And this potentiometer, variable resistor, is a 50 kilo ohm, 50,000 ohms. It has a funny taper to it. I did a little research on the internet, and I'll copy you on some links that will elaborate on this and give credit to people that have figured out some of this. When you turn this volume control up just a little bit, going from 0 to 1, it's a big chunk of the resistance change that it has capable. So when I go from 0 to 1, I've eaten up maybe a quarter of the total resistance or more. And then when I go up to, say, 2, 3, you notice almost no difference in volume. And almost going up to 10, you don't even really notice that much of an increase in volume. So one of the great mods that I saw detailed was to, on paper, just leave this here and put in a variable resistance here where there was a fixed 470 kilo ohm resistor. Change this to a 500 kilo ohm master volume control. I think that's a great idea. It kills two birds with one stone. The one problem is the way this is set up. This is just way too sensitive. And the other problem is the popping when you turn it on and off. So if I mount a master volume control right about here, thrust the leads in to where they need to go as shown in that circuit, and I'll break out a picture for you to look at. I think it's a great idea to make that be the master volume control. And another idea that I saw was to have a switch on the back of that would basically cut out the power amp so that you don't get any popping when you turn on and off the amp. I did a bunch of things verifying that when I put an adapter plug 1/8 inch to 1/4 inch in here with nothing plugged into it, into the power amp in, it sort of breaks the circuit so that nothing's going into the power amp. And when I do that and I turn on and off the amp, I don't get the popping. So this will essentially be that kind of thing. The switch will act in the same way, and I won't have to chain a plug that I have to put in here every time I want to turn on and off the amp. I will have to dial up the volume in the back, but it gives me more control over the volume if I use the right taper on that potentiometer, and the switch makes it so that I don't have the popping sound. In order to check the health of the amplifier, I want to make some voltage measurements. I have the schematic, and it tells me the conditions for making those measurements, and it has the test point voltages around here. So I need to generate a 5 millivolt AC input signal that the note here tells me should be at 1 kilohertz, 1,000 cycles per second. So a little bit later I'll talk about that more. I want to inject that signal here into the J1 and then trace through the circuitry and make sure that the voltages are proper. Now the reason for doing that is, I've replaced the Footswitch. I want to tackle the popping noise when the amp is turned on and off. But I also want to make sure that even though this amp is kind of known for having extreme sensitivity on the volume control between 0 and 1, that's where you get most of your range. I want to make sure, even though this is behaving that way and that's known, it's consistent with what most people experience, I want to make sure that it's in good health. Doesn't hurt. Let's see. So, in order to generate the 1 kilohertz signal I'm going to put in here, and what I'll do is you take your DVM, digital voltmeter, you turn it on, put it on the AC scale, and ground one lead, and then go through and carefully probe the others. Hey, this is a good time to point out there are lethal voltages in here, so if you don't know what you're doing, don't try any of this. There's the one hand rule. So typically what I'll do is I'll use an alligator clip to connect this to here, and I'll put one hand in my pocket, reminds me of a song, and I'll probe with the other hand. The reason for doing that is to make it so that there's no easy path through your heart. If you should get a shock, you don't want it to go through your heart, go into defib. With that out of the way, how do I get the 1 kilohertz signal? Well, I dragged out the trusty old op-amp designer. I use its internal function generator to create the 1 kilohertz signal. And I do it this way. It has the built-in 500 hertz capability, but by putting the switch to external, I can use a capacitor of my choice to set the frequency. And I found that a 0.05 microfarad capacitor will set 1 kilohertz for the frequency. This has the unwanted characteristic that the voltage coming out of it isn't symmetrically centered around ground. And so rather than use it that way, I chose to use a decoupling capacitor, which is a 0.47 microfarad, tubular in this case, and that lets through the AC component and it blocks the DC. And the trace looks pretty good. I also use the built-in potentiometer to adjust the gain or the voltage level that I'm actually taking out. So here's the lead to the oscilloscope. And the oscilloscope shows the trace where it's about 5 divisions top to bottom, and it's centered around ground. Let's see, there's ground. So it is telling me that it's 10 millivolts peak to peak. So I got to run through the calculation, dig out the formula for converting peak to peak voltage to RMS, but I know it's going to be pretty close to the 5 millivolt RMS that I'm looking for. So we'll tweak it as needed. And then here's the volume control doing its thing. When I get my hand in here, it kind of aggravates, it makes it angry. But it's a pretty clean looking signal. So I can inject that into J1 and then trace the voltages through the schematic. This is that potentiometer I was talking about. That's what I use to make the trace higher in voltage and then back down. So that's it. Just kind of using the tools that I have available to pretty easily inject a signal and do my voltage measurements. So I don't need to take the board out of the chassis in order to make these voltage measurements. I will need to do it when I change out the electrolytic capacitors. Another thing I'm doing to just eliminate any hum that comes from aging electrolytic capacitors in the power supply. Before I can do these measurements, I've got to be able to hook this up to a load. What's recommended on the schematic is an 8 ohm load, and based on the set points I'm going to be running at to make the measurements, I figure I'm going to need about a 10 watt resistor. So I need about an 8 ohm 10 watt resistor. The 8 ohm is like the speaker, only they want a resistive load. So here's a beefy high power resistor. It's 1 ohm. It's not enough. Here is a beefy power resistor. It's 27 ohms. Too much. Got the Goldilocks thing going on here. This will handle 55 watts. And this is one of the early Dale resistors. I picked up a lot of this stuff from a ham radio operator years ago. More years ago than I care to admit. This is actually a choke, which is another name for an inductor. It might actually have a resistance value similar to what I need, but I don't want to mess with it because it's a perfectly good choke. I don't want to burn it out. I don't know what the power dissipation is. I have another resistor. See if I can find it quick. This is a later model Dale resistor, and it's also a 1 ohm. So, you know, this is a 10 watt 1 ohm, and this is a 1 ohm that's got to be, I don't know, 100 watts, whatever. So that would give me 2 ohms, but I'm still short by a factor of 4. So I'm going to dig through some of my other pack rat stuff that I've got categorized and see if I can find something close to 8 to 10 ohms. And if I can't, I'll order the piece. I've already got electrolytics on order for replacing these two big honking 2200 microfarad electrolytics for the power supply. To change those out, I will have to pull the board. But I went ahead and ordered a few extras because there's a smattering of electrolytic capacitors in here that look a little cheesy. There's one here, and I'm thinking I should replace a few of those while I'm at it. Caps go bad over time, and they cause most of the troubles that I've experienced with older circuitry. Ciao. Hey, so I found another resistor. This is a 50 ohm, and I was thinking maybe if I put it in parallel with this 27 that it would do some good, and I was going to calculate what it would result in, and then I realized, well, look, just cut to the chase and measure it. So I put them in parallel, and when they're in parallel I get 24 ohm. So that it doesn't do it. I also have this other, this is a 40 kilo ohm. That's not going to do any good for me. Must be really fine wire. Yeah, so here's what it gets down to. I'll be buying an 8 ohm resistor to act as a load. I may as well get a 10 watt, something like that. You know, you can accomplish this with like a light bulb sometimes if you get the right filament resistance. I doubt that I'm in the right neighborhood. They also change resistance as a function of temperature. So, you know, unless this light bulb right here happens to be, let's say 6 ohms, and then at 10 watts it heats up to be 8 ohms. Sounds dandy, but I think I'd still like to have the power resistor on hand so I can just clip onto it and know what it's going to be. Hey, I've got things fired up to make some voltage measurements. You can hear the transformer buzz in the background. It's a little annoying, but it's pretty typical. I'm probing test point 12, which is supposed to be 95 millivolts, and I'm getting 52 right there. I have a 5 millivolt RMS signal coming in on jack 1, and I have all the pots set where they're supposed to be. So and they ask you to be running on the drive channel, which I found interesting. If I go clean, kind of curious what that does instead of drive. Same test point shows 51.6 millivolts. So I thought I'd play with the gain knob on the drive channel, which is where I'm supposed to be running. And when you turn it up, just a nice visual indication of how much power you're actually dissipating when you're running with a 65 watt guitar amp. So I have to reconcile my measurements to what I'm seeing here. I'll check a few more test points and see if I can identify where things are going south. Now I've adjusted the input to the amp to give me exactly 5 millivolts right here at the input to jack 1 with the meter. And as I go through, I expect 18.6 on pin 1 of U1. And instead of 18.6, I've got 23.5, which is close. Pin 1 of U2, I've got 128 millivolts instead of 95. Again, close, a little high. Not sure what's going on. And then, let's see. If I look at pin 7 of U1B, got 9 millivolts, supposed to be 7.8, not too far off. So I'll keep going through like this and getting a sense of how the amp's performing. After making a ton of voltage measurements, I found the output of U3, 250 millivolts as it's supposed to be, but the output of the first stage of the power amplifier is 8 times what it should be. And I really delved into making measurements, voltage measurements, looking at the signal coming through with the oscilloscope, etc. And what I've kind of come down to is, this is the reason this amp is notorious for having really high volume at low settings on the volume controls. So, since it seems pretty healthy, and there's just a disagreement between what the schematic says and what I'm getting, I'm going to go with the master volume control solution. Put it through the back panel. I'm going to pop a hole in here, use the switch to disconnect the preamp from the amp when I'm shutting it off so I don't get the popping sound. This will, as a master volume control, will allow me to have control beyond what I get from the clean and even the drive channel volume controls. And I also bought a tank, reverb tank, that is appropriate for this amplifier. That should take care of the reverb issue. I desoldered the electrolytics, the big ones, the 2200 microfarads, and replaced them over here. And that went pretty well. And now I've removed R47, and I will be putting in twisted pair to go from here to the volume control, the master volume. Give you an idea how we get twisted pair out of individual wires. This method works pretty well if you give it a nice tug after you've got it coiled up. Pretty nice. If I'm going to be able to fit these wires through these little holes that the resistor was in, I have to be sure to clean off the flux from where I removed the resistor. And I have to make sure that something like the lead of this resistor will pass through. Clean out that hole by running a resistor lead through it. That way I should be able to get the wire leads through. I've got a little flux on here, and bring in some solder. Get a nice hot solder joint. So now I can take the twisted pair, and that'll run over to the potentiometer that I'm putting in on the chassis. Alright, it's time to make some modifications to the chassis. Want to be able to fit in this master volume control. Going to pop a hole in over here, and I'll show you how I'm going to do that. Also, I wanted to point out that I tied down the heatsink that is used for the power transistors. I didn't want it flying around while I was messing around with the chassis. And let's roll. Now, the way I tied down the heatsink bar was simply to take 3 nuts and put the screws back in. Instead of going into the tap holes in the PCB heat spreader, the screws just go to these nuts. That keeps this in place and keeps me from getting silicone grease all over the place. So that's how I'm keeping that out of trouble while I do some modifications to the chassis. One thing I learned quite some time ago is a lot of technology and technical work is getting fixturing that will make life easier. So this is temporary fixturing. I just took a piece of plywood that is 3/4 inch thick, happens to be cut at a uniform width of about 3 inches, and because it sticks out a long ways, it allows me to support the back end of this chassis so it can just set here while I do the final markup to place the holes for the control. And in the spirit of measuring twice and cutting once, or maybe measuring a lot more than twice and just cutting once, here are the numbers. This is about a 5/16 diameter thread. So I need something on the order of 320 thousandths of an inch to get that through. I have a counterbore, which is my preferred way of machining really fine wood and also sheet metal, that measures about 330 thousandths of an inch. So that works. So in other words, it's a healthy clearance hole for the threaded boss on this control. And then I've got this little anti-rotation nub over here, and I'll go ahead and drill a hole for that. It wants to be about 1/8 of an inch in diameter, and it wants to be some distance from the center of this. It's not easy to measure, so if I measure across, remember this is about 5/16, so call it 310. And then if I measure over to the outside of this thing, I get about 630. All in all, when I do the math, it seems like I need about 450 thousandths, or just under 1/2 inch, from the center of the control shaft to the center of this tang over here. And I can accomplish that by laying it out carefully here on the chassis. It's, by definition, going to be kind of hard to see this. I have some auxiliary light I can shed on that. I don't know if that helps much. But I've laid out a mark for the center of my shaft, and then I had an errant mark over here, and then the right one at about 450 thousandths or so from the center of the shaft. So we are laid out with scribed lines, and I'll go in and center punch those and start off by drilling small pilot holes. The counterbore requires a pilot hole of, let's see, just a little over 200 thousandths of an inch. So I'll have to find a number drill that's close to 205 thousandths. That'll be my pilot hole for the counterbore to then open up and give me my shaft clearance. And then it's an 1/8 inch hole over here for the little tang that sticks up. Okay, I've center punched my 2 holes. I found a drill bit that's pretty close to 1/8 inch. I can't find my actual 1/8 inch drill bit, but this is a number drill that's very close. It measures like 126 or something. And I can start both holes with this. Using a counterbore to drill larger holes in sheet metal is something I learned years ago. The beauty of using the counterbore is it bears on the surface that you're machining instead of grabbing into it. So unlike the way a twist drill will bite into the workpiece, especially as it breaks through, a counterbore is pushing against the workpiece the whole time. And it makes it a little bit easier to control. As you get to larger drill bits, you want to run them slower. And that's really true of the counterbore that I'm about to use. Let's see. I may get away without having to use lubricant here. These cut really smooth, and you have much less concern about grabbing the workpiece as you break through. I also use these for headstock tuner changeouts. One thing that can happen is if you break it free, you can end up just having a washer down there that spins. There we go. That's broken through, and you get a pretty decent hole. Really quite clean, very little burr. Next, it's a little dry fit to make sure that the control fits in here, and it goes in just as slick as you can imagine. So the tab is here, sits flush on the inside of the panel. Rather a good job. I wanted to know how much of this shaft to cut off of the control that I'm adding to the back panel as a master volume. So I found a knob that's okay. It's not a perfect match for the ones here, but it's sort of in a similar style. And I like the idea of this sort of round with a little pointer. So it'll go back here, and I measured the depth of this, and if I just eyeball it to be flush with the skirt of this knob, I get about 660 thousandths, and that's going to have me putting it right about like this, with the if the pointer's like this, so I know I'll want it flat on the other side of the shaft kind of thing. And then, because it's all the way off, and then we turn it all the way on, and we go to 11. So 672. So it turns out that the end of this tab is roughly flush with the surface of the chassis. So I marked this 672 from here, just measured from the end of the tab. Eyeballed it, pencil marked it, and then put the Sharpie, and that's around 650 that I've got shown there. And that will get completely swallowed into the knob. And then I've got one kind of feeble set screw coming over from the side. They're 440s. It was missing the other one, which is going to be against the flat on the shaft. And I'm just using a 440 socket head, so I can get enough length and crank it down and not worry about finding an exact. I can always retrofit it with a set screw if I need to. So now it's time to do a little hacksawing, and it's always good to do a fierce forward thrust to mark the spot. Something like that. Now, I don't want it to drop onto the table. So, excuse my arms, and I'm going to catch it so it doesn't fall. Old school. So I kind of had second thoughts about using a Dremel tool to put a flat on this shaft, because that would be an abrasive thing, throwing a lot of debris, and it might get into the control. I want this to stay good, so I need about an 1/8 inch to take that 440. And I marked the shaft where I'm going to need it by just cranking the set screw down in the correct orientation. So this file is about 1/8 of an inch thick. And if I can get the location about right, I should be able to get some relief. Nice little flat to, I don't know if you can see it there. Nice little flat to take that set screw. We'll be in business there. I'll get you closer to this. Hey, so there it is in all its glory. This is my new master volume control, and it will be fed, the variable resistor part will be fed by this twisted pair. I've got to solder in the other twisted pair for the on-off switch. That's next. We are about to separate R48 from R49. We want the spot where the two resistors tie together. One's a 1 kilo ohm, the other's a 100 kilo ohm resistor. They tie together. Okay, here's R48 and R49. I want to lift this lead of R49. So it hit me that I should probably be prudent and use a little flux and wick to remove some of the solder before I attempt to pop R49 free from the board on that one end. So that's got most of the solder off of there. It may be enough to actually free that end up without putting any more heat. This is going to be a little hard to see, but this end of the resistor, that lead is free from the board. I managed to get it out without doing any damage. I'm going to solder one of the leads to here and one of the leads to there from my twisted pair. Sorry about all the motion there. I need more high-tech gizmos for photography. So
Yeah, one lead goes on the resistor, one lead goes into the board. So what I'm basically doing is breaking the tie point between the preamp and the amp, and I'm putting the switch in series with that. Okay, so what I plan to do is put the yellow lead into the board. I'll have to document this, and I'm not going to tin that. As long as I got a tight bundle, I can get it through the board easier without tinning it first. And I'm going to tin the blue lead because that's going to go to the resistor, and I want to get a nice, what do you call it, hook or hook eye or something like that. You make a J shape out of the wire, and a little bit of a J shape on the resistor lead, and hook them together. So I should be able to do it with regular needle nose pliers. And I want to put a shrink tubing down over that, which is complicated by the fact that I've got the twisted pair here. So I need a short length to go on here before I hook it to the resistor. This is not the most graceful soldering in the world, but I think I've got a mechanically secure connection there between the blue wire and the resistor lead, and I just need to flow a little solder on here without it shifting too much. Looks like a good solid joint. And then get the sleeving down there before it melts on its own. And then well, it's good to have a lighter, but if you're really careful with the soldering iron, you can get it to melt. I'm not going to add the pressure to myself to do it on camera. Alright, I got a good shrink on the tubing on the other side. I need to get the yellow wire coming through the board. I need to get this to flow. That means I need to add a little flux first. I did the same trick as I showed you earlier with pressing through a resistor lead through the board to get nice clearance through the hole so the wire will slip through easily. There she is, and I just need to clean that up a little bit. One way to get shielding for an impromptu cable like this is to strip apart some guitar cable. You get the outer sheath off, this rubber. This was a cable that wasn't in very good shape. It had a resistive connection somewhere. It had like a 4 ohm resistance. It should have been like less than 1 ohm. So I took out the outer sheath by cutting it lengthwise with an X-Acto very carefully. And then once I got it to the point where this was free, I did the, when you push the stuff and there's no longer any wrapper around it, it expands in diameter. And it was pretty easy to get the central core out. This is the insulator and the central conductor from the cable. Then you're left with this shield. Now I can't just leave it bare metal in there. The idea is I'll connect it on one end only to chassis ground. Even though I've got twisted pairs, I won't get complete rejection of noise due to common mode because, well, anyway, the shielding should help. So, let's see. The next step is to put some heat shrink around it and, well, check my measurements and stuff. The idea I have going on is I want to use a cable clamp on this extra tall screw I've arranged for here. And this will dress through there and then make it up to the potentiometer and switch. So I just have to get the lengths right so that everything works out, and get shrink tubing on this so that it doesn't short anything out. Here's the cable coming from the PC board that's going to the control, and that's the shielded cable. I've written down which signals are going where. So the orange wire is going to the inverting input of the U3. The green wire is the one that goes over here
to the C32. I'm wiring this up so that the resistance increases as I go clockwise. And I also noted that the yellow and blue wires are the ones that are going to the switch that connect this point to that point. Over here, this is an audio taper 500K pot, and not sure you can see the reading real well. I've put it on this range so I don't get that annoying beep. As I turn the switch on and rotate the potentiometer, I go, now I need to go to auto range. There we go. I'm at about 60K, and I've gone a little over halfway, half of the rotation. So let's see. That's about a quarter turn. I've gone to about 50K. And when I get to the very end, I'm at almost 500K, 450. So if I take a quarter turn back from that, there's a lot of change right in that region there. So this is sort of the opposite of the potentiometer that was used in the original volume control. And what I need to do is span these two lugs together, and I've chosen to do it that way instead of just having a floating end on this. It's usually not a good idea. So by just bridging these two together, I have a common tie point. The wiper goes from starting at this lug around like this in a clockwise rotation to the full resistance. This is on the wiper. So the wiper starts out real nearby at low resistance and it goes far away to higher resistance. And then these two just stay ganged together. So I'm going to do that with the lead of a resistor. The resistor is going to give me 1 kilo still in series, still in place on that feedback, rather than going to a 0 ohm feedback resistance. We'll give that a try. Here's the control all wired up, and I only used shrink tube here where I needed to cover up that resistor a little bit. I think these are good solder joints, and it's wide open in here. I'm thinking shrink tubing over the terminals on the controller aren't really necessary. So this is the shield. I've connected a black wire to the shield that runs down the cable, and I want to leave a little service loop, and I'm going to drill another hole, another small one in here, and use a lug to where'd my lug go? Use a lug to make contact to a small screw going through there. It'll be on the shiny aluminum side and it'll make good contact with ground. I laid out a hole for the 440 screw to attach the ground lug. It's about 1 1/8 inches over from the center of the control hole. It's on that same line. I've already scribed and center punched. So this is the control installed. Ground lug over here. There's the control. Let me flip this up. Looks pretty sharp. I might replace that socket head with a set screw or a shorter socket head. But I'm pretty happy with this mod, and it's time to put things back together. Hey. Have things powered up. I brought it up slowly, making sure everything was okay. I'm back where I was. The master volume is all the way up. So on pin 1 of U3, I'm seeing 250 millivolts. And on pin 6 of U5, I'm seeing 23 volts. Just like the old days. But now, I have a nice smooth control that lets me get down to 3 volts, which is what I should be getting here. 2.86, etc. And it does affect voltage here. It's no longer 250 millivolts, of course. It's about 60 millivolts now. And I'm thrilled. Turn it all the way down, turn it back up, attach the speaker, and really put it through its paces. Okay, I've hooked up the speakers with clip leads before I put everything all back together. I have the 1 kilohertz function generator going. I've got it piped into here. Same conditions as ever, but I've turned the gain down on the gain channel. No, it's actually in the same spot, but I've turned the master volume control down. So that's with the master volume control almost all the way down. It really gets ear piercing. That was the problem with the volume. So let's see. I should also be able to show that when I turn the master volume control volume down and the switch off, it doesn't pop the speakers anymore. So let's give that a try. Much smaller pop. I think I can live with that. Yeah, that's much less than it used to be. We'll put it through its paces with the guitar. I'll try and do a quick A/B comparison with the master volume control set all the way up. That's the same as the situation was before. It's both too loud, it has that on and off junk. So setting the volume to about 1. I can play more or less like this. Nasty. It's a good sounding amp though. This is a clean channel obviously. If I do go to the drive channel, let's see. I just gotta be way down the gain there. And then you're not getting the results you want. It's just too loud to be able to, I don't know how to put it in words, but with the master volume control turned down, so we're less than 12 o'clock. There we go, about 12 o'clock. So now I can bring the gain back up. That's better. And when I want to turn off the power, go all the way down on the power amp gain, turn off the power amp with that click on the switch, and it's a nice quiet turn off. Nice quiet turn on. Then you bring it back to life with the master volume control. Go back to clean. I can move this up to about 3 or 2 or whatever. That's about 2. Much better. So here's a demo of the Footswitch. I've got a standard Footswitch plugged in now to the repaired Footswitch jack. Here's clean. So that's working great. All told, I'm really happy with the way this is now. It's great for gigging, for small, mic'd up, and it's good for rehearsal, practice. I'm really liking this amp again.